Hi boys and girls, it's nighttime here at the Berman household and I'm trying to keep my voice down because I'm directly beneath my sleeping son who we just finally got to sleep. So like I told you guys in class, this is your lesson for you to take notes from. We're talking about lines of symmetry and rotational symmetry for lesson 6.5. I personally think this stuff, if you understand what we're talking about with the word symmetry, you'll find it to be quite easy. So line symmetry is exactly what it says here. It exists if a figure can be folded over a line so that one half of the figure matches the other half. This line that we fold on is called the line of symmetry. So you've heard of this stuff before. In the first example, we have a star, and we're supposed to draw all of the lines of symmetry. Now remember that lines of symmetry are that place where you can fold, and I'll use these dashed lines, where you can fold a figure on this dashed line, and when you do that, it exactly folds across the star. So that's something that we have with lines of symmetry. So here's one of the lines. It went from a point straight down. Now it's going to be hard for me to do without tilting my head, so I'm going to tilt my head. And this is another line. Now it's not perfectly straight, but you guys would want to probably use a ruler. Let's go the other way. So that's the third line. Might as well go this way now. And I know I look like a dork right now, so you don't have to tell me. And then we go this way. And they fold exactly onto themselves every single time on these lines. So again, there's 1, 2, 3, 4, 5 lines for each one of the points here. So it's 1, 2, 3, 4, 5 points. So it has 5 lines of symmetry. Wow. Computer's kind of slow at my house. Lines of symmetry. And again, that's because that they fold onto themselves. Okay? Now, the next kind of symmetry is called rotational symmetry. And just like the words up here say, now you might want to paraphrase this, but what we're going to do is we're going to take shapes and we're just going to pretty much, if you can imagine, taking them, pulling them off the piece of paper and then rotating, and they need to look exactly the same way as we rotate them. So this flower looking shape, we're looking for it having rotational symmetry. So if I take this whole thing, and again, if I just pick it up and then rotate it, you can see that if I rotate it 90 degrees this way, it's going to fall exactly back onto itself. So our job is to determine if the figure has rotational symmetry. It does, because it looks exactly the same as I rotate the shape. So how many, name the angle of rotation? Well, it's every 90 degrees. So I have 4 times before it falls exactly on itself again. Because if I started right here and then I rotate, now that's going to be, those marks are going to be over on this side, and then they'll be on the bottom, and then they'll be on the left side. And that again, folks, is our rotational symmetry. So at 90 degrees, at 180 degrees, at 270, I just keep adding 90 degrees every single time. And then of course every shape has 360 degrees because it falls back on itself again like a full circle. So that's what rotational symmetry is. Alright, this will be the last thing that we have to look at for our notes, and our job is to say which shapes have rotational symmetry. So if I were to take this heart and rotate it, how long do I have to rotate it before it lands on itself? Now, see if I can do this with a computer. Oh yeah. So this would be 90 degrees. Oh, here's my cat. 180 degrees, 270, and now it looks back the same again at 360 degrees. See ya, kitty? Kind of weird. So this one does not have rotational symmetry. Now neither does the arrow because it's the exact same thing. It only is pointing upward. Now this diamond looking shape over here does have rotational symmetry because if I rotate it a full 180 degrees, it looks exactly the same again. So this one's a big fat yes. Oh, I screwed it up. So this one's a yes. Those two were no. And this one down here is also a yes if it's a perfect regular pentagon. Now personally, this one does not look like it's a regular pentagon because it looks like it's a little bit fatter, like it's been squished down. I think the purpose of this one was to say that it's going to have rotational symmetry. Oh, here's my cat again. Get your butt out of here. My kids don't want to see you. Yeah, I know. Get out. And so I would say that there should be 360 divided by 5, and she's coming back again. Oh, meow. Just sit then, okay? Sit. You can talk to the kids. So the 360 degrees divided by 5 would be the number of degrees that we'd have to rotate it to get to each rotational symmetry. Same thing with this guy. There's 5 points, so it's going to rotate up from here to here, and it's going to keep rotating and looking exactly the same. So these two should be a yes as long as they are perfectly the same shape. And I'm not going to get too picky because I personally think that the pentagon is not because it's fat, but I believe that the purpose of this lesson was to show you that it is. Alright folks, so this is what you got to do for today. Good luck. I'm opening up the App Store for some reason. Toodles.